Hi students, welcome to this video. This is about CS 8351 Digital Principles and System Design, and we are discussing the second unit, combinational circuit. This is your Professor G. Ilangovan, Department of Computer Science and Engineering, NPR College of Engineering and Technology. So in today's video, we are going to discuss about binary adders. Under the binary adders, what are the off adder and full adder, and about the subtractor in subtractor, off adder, off subtractor and full subtractor. This is what we are going to understand in this video. So in generally, what is a binary adder and subtractor? So this binary adder and subtractor is capable of performing addition in the binary adder, subtraction in the binary subtractor. So there is a difference between logical addition and binary addition. 1 plus 1 is 1 in logical addition, but in binary addition, 1 plus 1 is equal to 1 0. So we need such a logical circuits. That kind of logical circuit we need to design. But in the digital environment, the binary adders and subtractors are very basic and essential building blocks to design and develop different kind of hardwares. So in that sense, we need to understand the off adder and full adder as well, off subtractor and full subtractor in this video. And what is an off adder? So how it differs from the full adder? Off adder in the sense, it's basically a combinational circuit which is capable of adding 2 bits, and it will generate 2 outputs. The 2 inputs are, one is from addend and one is other one from the organ, and the output, there is a 2 outputs, one is in sum, another one is in carry. For example, if you are adding 1 and 1, we will get output 1 0. In the 0 is called as in sum, and where the new bit generated from the single bits is called in carry. So carry is the sense it is carrying the value to the higher order. So if you wanted to see in a basic circuit diagram, it will be looks like this. There is 2 inputs A and B to the off adder, and it generates 2 outputs. One is called sum, another one is called carry. So the truth table we can draw as the 2 inputs A and B and carry and sum. And when both the things are 0 0, if you are adding 2 zeros, the sum is 0, carry is also 0. If you are adding 0 plus 1, the sum is 1, it does not generate any carry, so the carry is 0. Or if you are adding 1 and 0, again the same, the output sum is going to be 1 and it does not generate a carry, so the carry is 0. But if you are adding 1 and 1, the sum is 0, now it introduced or it generated a carry 1. So this is the truth table. So you will just recollect the design procedure. So the circuit specification is given, variables are assigned, truth table are drawn. Next step is draw the Boolean expression for each variable. So sum and carry, and draw the circuit diagram. Now you just have a deep look on that carry. If you are having carry alone, if you are comparing that, it looks like an AND gate output. And if you are looking the sum output alone with respect to the input A and B, it looks like, yes, it looks like XOR output. So the expression, even if you are using the K-map also, you will be ending with carry is equal to A dot B, an AND gate, and sum is equal to A B dash plus A dash B, an XOR operation. So the circuit diagram, AB as the input, and one XOR gate gives us sum, one AND gate gives us carry. So this is the off adder circuit diagram. So we followed the all the four steps in the design principle. But it is well established in circuit and off adder. Next one is in full adder. So what makes the difference between off adder and full adder? Again, if you are seeing in general, it is also going to generate the two outputs. The two outputs are sum and carry. But if you are looking at the inputs, uh, generally it may referred as a three input, but strictly speaking, the inputs are two. The other input is generated carry from the lower order sum. So a two input, two number addition with considering the lower order carry. So that makes the full adder. So the off adder and full adder, the senses, off adder does not consider the carry generated from the lower sum, lower order sum. But full adder, it will consider that. So it is somehow it is meaningful saying it has three inputs and two outputs. So the circuit diagram will looks like this. The A and B is the two numbers. One is addend, another one is argand. And C in is the previous bit, lower order bit summation. If it was generated a carry, that carry is passed to this. That carry might be a 0 or 1, that is different issue, but it consider that carry. And it generates a two output, one is in sum output, another one is in carry output. So to construct an output, there are three inputs. We will call the inputs are A, B and C in, and two outputs, sum and carry. So now assume all the three as 0. The addend and argand bits are 0 and lower order sum is also 0. So the sum is 0 and carry is 0. And if previous lower order carry alone is 1, the A and B is 0. So sum is 1, carry, there is no carry. And the same thing for 0, 1, 0. And if B is 1 and carry input is 1 and A is 0, now the result is 1, 0, that is sum is 0, carry is 1. And now also there is no carry. Now either A or B is 1 along with C input is 1, definitely there will be a carry and sum is 0. There is no carry and A and B both are 1, now also it generates and carry and sum is 0. If all the three is 1, the sum is 1 and carry is 1. Now we got the truth table. Now get the expression for sum and carry with the help of KMAP. So we will get carry output as AB plus AC in plus BC in, and sum output is like this. So sum output and carry output. We will be getting the sum output will be like this and carry output will be like this. Now it looks like some bigger circuit. We already said that the full adder, off adder, that and all is a basic building blocks for a number of logical circuits in while implementing the hardware. So we are trying to find out, is there any possibility of having reduced or minimum expressions? So this kind of circuit, we are trying to reduce the circuits. So we are trying to minimize the logical circuit in different way. Is it possible to reduce in simplified manner? So this is one of the simplified expression. That is, we are trying to implement the full adder with the help of off adder. So the name itself suggests that if you are adding two off adders, we will get a full adder. So that possibility we are looking. So with the help of this simplified Boolean expression, we got simplified that. So the sum and carry we got like this. So there is two off adders and the output, the XOR output of first off adder is given to the second off adder, and final output will be the sum. And both carry from the both off adder is combined together with an OR gate, will get an output. So this is then so simplified uh, full adder circuit with the help of two off adders. So two off adders we are adding. This also we can give in a block diagram representation how it has been generated. And the next thing is subtractor. So in the subtractor, again we will be having off subtractor and full subtractor. So here also we are saying that off subtractor does not consider lower order borrow, and full subtractor is going to consider lower order borrow. The similar derivation from the off adder, from the off subtractor, how to get the full subtractor. That's our goal here now. So the off subtractor is, so two inputs and two outputs are called, one is an difference, another one is an borrow. So the truth table is the two inputs A and B and outputs difference and borrow. And if both the thing is 0, 0, the inputs are 0 and difference is 0, output is 0. But if 0 and 1 is there, 0 minus 1 is not equal to 1 minus 0. Please keep it in your mind. 0 minus 1 is differ from 1 minus 0. So 0 minus 1, we need to borrow 1. So that's what borrow is 1. Difference is also 1. And when you are doing 1 minus 0, the difference is 1 and borrow is 0. We are not borrowing. That's what I specifically mentioned, that 0 minus 1 is different from 1 minus 0. And 1 minus 1 is difference is 0, borrow is also 0. Now construct the K-map for difference and borrow to get the Boolean expression. So from that we can say the difference is an XOR gate and borrow is A dash dot B. And now if you are looking at the difference and sum, both are equal. So subtraction or adding, in both the cases, difference or sum will be the same. And the borrow or carry is also same, but only the difference is one of the input is inverted input. Otherwise, it is also looks like an off adder. So this is the off subtractor we have implemented. So similarly, we have to implement the full subtractor. So in the full subtractor, again, it is going to have three inputs. One input is the lower order borrow while subtracting. But in the full subtraction, it was not considered. So the output is again only two output, difference and borrow. It shows the circuit diagram. A and B as a available input values, and B input is lower order borrow when doing the subtraction, and the result is difference and borrow out. The truth table again, so there is three inputs, A, B and B in, and difference and borrow output. So this is what the truth table for the full subtractor. So to design the circuit, again we have to construct the K-map for difference and borrow output separately. From that we will be getting the Boolean expression. So if you are straight away implementing the circuit, it again coming like this, and you can see that the different circuit is similar to that uh, uh, sum circuit, and similarly here also it's a different circuit. Now we wanted to implement the full subtractor by using the two off subtractor. For that we will be applying the same adoption rules. So we'll be getting the difference by combining all the things. So you'll be getting the difference as this thing and borrow as like this. Now with the help of two off subtractor, we can implement a full subtractor. Similarly, the A and B is given, the difference output is given as input to another difference. So the second off adder output will be the straight away the difference of the circuit, and first borrow output and second borrow output is combined. That is first off subtractor borrow, second off subtractor borrow. Both the thing is given to an OR gate. So we'll be getting an full subtractor. So dear students, in this video we got understood about binary adder, in that off adder, full adder, and subtractor, in that off subtractor and full subtractor. So with this, bye from Professor J. Ilangovan. We'll discuss some other things in the next video. Thank you. Good day. Bye.